In the previous video, we saw that the solutions to the Lejeune ordinary differential equations are the Lejeune polynomials. Now in this video, we'll actually describe better ways of giving the polynomial to any degree. So LPs are my abbreviation from in the future for the so-called Lejeune polynomials. The small aside on the pronunciation of Lejeune, he was a French mathematician, and although that it's pronounced by most people as Legendre or Legendre, it's actually Lejeune. So I'm going to just stick to the proper pronunciation, although you're free to pronounce it any way you want, because it's the content and not the grammar that's important here. So there are two ways of talking about the polynomial solutions of the Lejeune ODE. One is by using what's called a generating function. A generating function is some sort of a potential that allows us to express the solutions to any ordinary differential equation by means of that potential. So this potential function is a very really celebrated potential function, and by the way, this is the reason why electrostatic potentials are expressible in terms of the Lejeune ODE, because of such potential functions. So they first arose in a study of electrostatics and physics, and indeed a lot of mathematics is inspired directly by physics. It turns out that if you expand this in powers of h, then the lth power has a coefficient that's exactly equal to the Lejeune polynomial of order L. So that's really great, because this is very easy to work with. It's just a series, and you can expand this series in powers of h, and you get different polynomials. Now each of these famous differential equations, in addition to having a generating function, which I'll abbreviate here GF, also has an associated formula known as the Rodriguez formula. And the Rodriguez formula can be directly derived from these generating functions. So you can get PLX as 1 over 2 to the L factorial dl over dxl, that means the lth derivative of x squared minus 1 to the power L. So that's also very convenient, because if I want to find what P1x is, I can apply this. If I want to find what P2x is, I just have to put L equals 2 there and find it out. So as a simple exercise, let's try what it would be like for L equals 2 to use the Rodriguez formula and see what we get. So P2x is going to be 1 over 2 squared, which is 4, 2 factorial, which is 2, so that's 1 over 8. Then I get d2 by dx squared, x squared minus 1 squared. So you can see that it is not exactly a picnic to do this. It's kind of a bear to apply this procedure. So let's try this for this easy enough that we can do it. Let's first do a d by dx of it. So d by dx of that is going to be 2 times x squared minus 1, and then you go and differentiate the inside function. That's going to be 2x. So the 2 and 2 is 4, which will cancel the 1 over 8 outside. So I get 1/2 d by dx x times x squared minus 1. So you see a little bit of what's going on here. The polynomial is getting whittled down in degree each time the d by dx acts on it. So let's see what happens when you differentiate once more. I get the d by dx, a product function, so I can either do it as x cubed minus x, or I can do it as x times x squared minus 1. I don't care which one I do it. Let me do it as x times x squared minus 1. So I'll get x squared minus 1, that's the first term, and then I do instead the second term, so I get 2x. So this gives me 1/2 x squared minus 1 plus 2x squared, which is 1/2 1 minus 1/2 I think I should have put 3x squared. So I get 3x squared minus 1. So that's the second one. Okay, and you can get them to any order using this. So that's a very convenient way of doing it, and you can also Taylor expand this if you like. It's a little bit more tricky because the Taylor expansion of -1/2 brings so you can use what's called the Newtonian binomial theorem approximation. I'll write it for any power. So that gives me x plus a. If you have x plus a and you take to the power n, here n is equal to -1/2, and x can be anything and a can be anything. So x is probably, you can think of x as 1 minus 2x h, and you can think of a as h squared. So this procedure will apply. So the Newtonian binomial theorem approximation tells you that, not approximation, theorem tells you that this is n times x to the n a plus n times n minus 1 over 2 factorial x to the n minus 1 a, and then you keep going like this. It stops at some point if n is an integer. If n is not an integer, you keep going like that. Okay, so it never stops. So this is the theorem of Newton, known as the binomial theorem, and the binomial theorem can be used to expand this to any order. Now, what is more interesting from the viewpoint of computation of these Lejeune polynomials to any order is the fact that we can actually get so-called recursion relations from the Rodriguez formula or from the generating function. In your homework, you will have opportunities to find recursion formulas from either of these two methods. But once these recursion formulas are available to us, we can use them to advantage. So a recursion formula is one that gives you a polynomial of higher order in terms of a polynomial of lower order. So let's think about the following one. LPL equals 2L minus 1 x PL minus 1 minus L minus 1 PL minus 2. So this is a good recursion formula to use if you know a lower polynomial, two lower polynomials. So if you know, for example, if you know P0 and P1, and you can do P0 and P1 using hard work, using the Rodriguez formula, and then you can find the rest using the recursion instead of dumbly differentiating each time to higher and higher degrees. It's pretty hard to do that. So it's possible for us to proceed. So let's try using this recursion formula. So let's assume that hard work gave us P0. It turns out that P0 equals 1. And that's actually not very hard to prove. P0 is equal to 1 over 2 to the 0. L factorial is 0 factorial, which is 1. And d to the power 0 over dx to the power 0 is again nothing. X squared minus 1 to the power 0 is again 1. So that's believable. That's believable. And then P1 equals x can be also found by directly doing it. I did it for P2, so P1 is actually easier to do than P2 is. So I'll leave it as an exercise for those who are curious to find out how much work is involved. And I can tell you it's about half as much work as the P2, obviously, because it's half the degree. So let's find out what P2 would be. We already know that P2 through hard work is this. So it might be good to find out what P2 through this recursion formula is. So L equals 2 now. So I'm getting 2 times P2 equals 2 times 2 minus 1 x P1, which is x, minus L minus 1, which is 2 minus 1, P0, P0, which is 1. Okay, so this is 2P2 equals 2 times 2 minus 1, 3 x squared. So you see, we're already there. Minus 1, or P2 equals 1/2 3x squared minus 1, which bears out the calculation we had earlier through the laborious Rodriguez formula. So this is a very useful technique indeed, just to see if we can get confidence on this one. let's try to get P3. The only disadvantage of this is you can't skip an order. You have to go systematically. If you want P5, you have to first go find P3. The advantage with this is if you want to find P5, you can directly stick this in the computer and find P5 for L equals 5. So computer program will immediately give you P5. Or this method will, you just have to look at the fifth coefficient, the coefficient of h to the power 5, and that will immediately give you P5. So this method is equally superior. But this method is good if you want to go slow and steady, step by step. You have to build up though. So let's try to get P4. But to get P4, we need to first get P3. So let's first try to get P3. Put L equals 3 next. So T3 times P3 is going to be 2 times 3 minus 1 x times P2 minus 3 minus 1 P L equals 3, so that's 3 minus 2 or 1. I always urge you to do a first step where you write the p's as is and don't go directly like I did there. So now I'm going to get 3 times P3 is equal to 5x times P2, and P2 is all of this, minus 2 times P1, which is x. So let's see if this can be simplified a little bit. That gives me 15 x cubed over 2 minus 5x over 2 minus 2x. Oh, before I forget, one other thing you have to observe here is that in an earlier video I mentioned that the polynomial you get is always going to match the L value. So this is a 0th order polynomial, and that's the first order polynomial. That's a second order polynomial, and so you can expect this to be a third order polynomial, a third order and even, first order and odd. So we showed that the alternating series converges. If it's 0, the 0th order polynomial, there's nothing to talk about here. But the first order polynomial, the odd series converges, the even series diverges. Here the even series converges, the odd series diverges. So only one series will converge. Now if you do this, taking common denominator and everything, I'm going to get 15 x cubed over 2 minus, that's 5x minus 4x, which is 9x. So that 9x over 2, all that is 3p3. So this tells me that p3 is the whole thing divided by 3. So that's 5 halves x cubed minus 3 halves x. So we've got our p3. Let me box this up. So we have some results here. And once you have P3 and P2, you can then proceed to find P4 by the same recursion relation. Another aside, there are several recursion relations. You can look it up and you'll be able to prove quite a few of these once you have facility with the Rodriguez formula and the generating function. But what we're going to do is only use the basic ones because we're just trying to get new polynomials, not show some crazy things between them. So L equals 4 is next. 4 times P4. So this is very robotic. Okay, it's very robotic and very relaxing. It's just quite a simple thing to do. 2 times 4 minus 1 and x P3 minus 4 minus 1 P2. And I won't spoil the fun for you. I'll leave it as an exercise for you to work this out. And if you cannot, you can always look at the notes. But this turns out to be something messy. So the 30x squared plus 3. Those who work with Lejeune polynomials sufficient number of times will remember all these values. For example, I remember 35 quite clearly because it shows up in the fourth order of the expansion of the electric potential.